also the grid, and then there's a different kind of grid. And Sebastian will tell us about electricity and energy, and moving things around with functional programming.
Thanks, Mike. Right, so I'm Sebastian Egner from a small company in Berlin, which is actually located in Berlin and Munich. It's called Intellios AG. And this is about grid computing, but not as you know. It's the power grid, actually.
And the microphone is not on.
It's not. It makes noise, but it doesn't carry my voice. Right, now it is. Right, the power grid and the power grid in national power grid. And since I'm from Germany, I'm largely talking about the German power grid as an example. If you're from the US, you magnify everything by 10, right? So now, what is a power grid? And the power grid, in the broadest possible terms, is like you have some producers or generation of energy, which could be coal or could be water or other things. And then you have a flow of electricity through the network. And the network in the power grid is the highest voltage network. And there are not different things, but think of 380 kilovolts. And then there are consumers of electricity. This is an oven or industrial facilities, homes, everything. And whenever you plug in your, whenever you plug in your computer like this, so you're connected to one of these facilities on the left. So now the thing is, in Germany, or not only in Germany, so whenever electricity flows here, you can't store these amount of electricity. So the electricity network has to be balanced. And that is essentially the task of, in Germany, 4 different companies who share a geographic area, which might be unconnected, and there are some strange exceptions even. And these companies make sure that at any time the amount of electrons that go into the wire come out at the other side. So I depict it like this. So you have a dynamic balance from the generation side to the consumption side. And now what do you do if it's not in balance? You can use this lever. It's called operating reserve power to balance it again, right? So these so-called TSOs, transmission system operators, they held an auction and they buy reserve power that they can use on demand. And what do they actually balance, or how do they balance? So there's a communication channel you've never heard of, and the communication channel is that in Germany we have 50 Hertz frequency on the network, and it's all in sync, yeah? And not in all countries it's in sync, but in this country it's in sync, and in fact, yeah, well, that's a big disadvantage if it isn't. But in Germany it's in sync, everything is linked to a specific clock, 50 Hertz. And if you think of a turbine, and a turbine driving a generator, the generator generates the 50 Hertz by revolving. Now if there is more load on the network, the generator has to work against more resistance, and that means that the net frequency goes down. And to give you an impression, it goes down, if it goes down by 1 Hertz, so outside this primary reserve range, it would mean 50 gigawatt. And I will tell you what a gigawatt is in a second. So, but the other thing is, there is an industry principle, and the industry principle says generation follows consumption. And that means you don't want to think about whether there is enough electricity in order to plug in your laptop. And you also don't want to do that if you switch on like a megawatt of power. Maybe if you do the latter, you need to make an advanced notice the day before. But you don't want to make your decision, base your decision on whether it's available. It should be available. So generation is made to follow consumption. And the way to do this is this operating reserve power, and there are 3 levels, which is unessential to this talk, but there are like small deviations, larger deviations, or longer deviations, and it's more complex than that. So now, what happens in the real world? The real world, like this, looked like this 30 years ago. Today, it looks like this. So you have renewable energy, and generation doesn't follow consumption, because wind and solar you can only dim down, you can't increase it on demand. So you can, and to give you an impression how much that makes a difference, in Germany we have about 11% renewables right now, and on August the 18th we had a 20 gigawatt peak in production. And that's only the amount, it doesn't tell you anything about the fluctuations, and the fluctuations are on the order of gigawatts a day. So it goes up and down every day, and so this is a problem. And now how do we deal with it? We have an increased fluctuation here, so this puts a strain on the operating reserve power. But there is another way. You can restore that by making the demand side also variable. And that is what is at the core of what the company I work for does. So generation follows consumption except for wind and solar, and demand response management. And that's what we do. We try to sort of reduce the load when energy is scarce. So, yeah, as an aside, in the US, that's a mature concept already. So, the market leader, Enernoc, did an IPO in 2007. In the US, the situation is completely different from Germany, strangely enough, because you have brownouts and blackouts, and due to the liberalization, which is far more advanced than in Germany, you need more demand-side management. You just need it. So if you go to a company, say, do you want to join our demand response program? You can say, okay, if you don't, you're just shut down when there's no electricity. So you can better do it with us than being shut down. Right? So that's a lot much easier say. So in our case, it's a little bit different. So we go there and say, okay, we don't touch your business at all. We look for flexibility. That doesn't hurt you at all. Yeah, and we give a recommendation. And if we say, okay, now you could earn money if you switch off these loads, then you can earn money with us, right? If you do it. And if you don't, that's fine with us. Yeah. Okay, and this means also there's an extremely complex body of national regulation. So if what I tell you about Germany doesn't mean anything about for Belgium, yeah, there's just completely different. Yeah? So, right. Now what is a gigawatt? This smart grid is largely associated with these things, like big black refrigerators, maybe they're white. Yeah? But it's not. So this demand-side management, you need to mind the order of magnitude. So here, a refrigerator has like 100 watt, and I put 3 orders of magnitudes between each of these things. So a mobile phone, an industrial climate control, an industrial arc furnace. So I've seen it, exactly this one. And for example, the national power grid. And so if you imagine from here to there, that's 9 orders of magnitude. So in order to do something visibly even with refrigerators, you need to take a lot of them. So now if you switch on-demand refrigerators, that would be possible. Yeah, it's technically feasible. You can do the telecommunication stuff and like that. But what we found when we did the initial business case was the cost of connecting one refrigerator is not so much different from the cost of connecting one industrial arc furnace. Now you can imagine why we are in this range and not in that. Right? The other thing is, like what is a gigawatt, is this is a de-rinding buffer. So you have a paper mill, and a paper mill takes trees essentially, gets rid of the rind, so it shaves it, and then it grinds it down. It's like, ooh, grind it down. Grinding down is energy expensive. And then, okay, but before it does that, the trees, the trunks are put somewhere. They are stored. Now, and this amount is about 1 day production. So 1 day production equals 200 megawatt hours in capacity. So this is a battery for me. And this is the reason why this whole thing could work. Now, what are the challenges in this whole endeavor? The first, knowing the rules of the game, that's this regulation thing. That's actually the hardest part and took us the longest time. The other thing is doing the actual business model. Like we sell A to B, who buy it because of C, and like what are A, B, and C actually. And the third, I put as the third, is finding industry participants. Why would they want to join us? And the interesting thing is we constantly call them customers, but they are our suppliers. They supply energy and get paid for it. But we need to get them to do that. So we have a sales process to find our suppliers. It's like reverse world. And well, there were countries in Germany that didn't like that. And what I put fourth, so it's a honorable fourth place, I would say, is the technology, because it's doable. You can use different technologies to do the same thing, but how efficiently and effectively you can use your technology really depends, and that's why I'm here. So I'm focusing now on the technology side, and the big question is, why FP? And maybe you can imagine that there's something left out. There's a short answer and a longer answer, and the short answer is, why not? And maybe this is the wrong place to ask, or to put it like that, because I'm preaching to the choir, but FP is mature, full stop. Yeah, and so why not? So instead of answering why did we use FP, I'm answering the question, why wouldn't we use FP? And there are a number of reasons in the power industry. For example, FP is still an unknown quantity. So people haven't heard it, or don't know, don't associate things with it, or like, okay. And then you can say, okay, let me explain what it is, and also let me explain what examples of what has been done with it. And then they start to link into it. And the other thing is, it's risky because it's not mainstream, which is always, it's the biggest hurdle, I would say, in general. But how risky was Java before it flushed out C++? It's the whole thing. I mean, and there are big companies who still don't want to get away from C++ for something different, because it has advantages for them. They have invested heavily in the technology and the basis, and why not? So we are a startup company, we don't carry so much baggage, and that allows us to be flexible on that side. No large technology partners. Well, Microsoft released F# for .NET. If you don't know what F# is, look up what F# is. If you don't know what Microsoft is, get out of the room. Okay, few experienced developers, that's not true anymore. All the people we interviewed for job interviews knew it from university. Suppliers don't use it. Well, they don't. I don't know how to counter that. Okay, but eventually at Intelios the honor is to the board. The board decided that we are going to use modern technology. It wasn't a formal decision in that sense. They did. Now is the time for a short introduction of the Intelios. So it was founded in 2010 by 3 people who have large industry experience, and for the not industry experience in the power industry, but in telecommunications, as Stefan Linders, it's the CTO, Oliver Stahl in marketing and also in technology, and Thomas Schulz as a venture capitalist originally. Not originally. Originally he's a computer scientist, but he did the longest time. And we were VC funded with a Series A completed in 2011. Now, it's still a small company, and we are in a sort of exploration mode. So we have an operation in place, but it still needs to grow, and we are still flexible in where it really takes us. The most important thing is what do we actually offer? And we offer production of electrical energy by intelligent management of industrial consumers. Now that's a whole mouthful, but essentially it comes down to what I said before, that we connect companies who, like paper mills, and we install something at their site. We call it an e-box, it's an embedded system. We communicate with this e-box all the time. And then we have a data center, and then the data center connected a network operation center where people manage the network, the electric network for us. And then if the TSOs say, okay, please send us more power now, then our people say, okay, this one is off, this one is available, and so on. They put it together, and they send a request out to all the participants, and the participants will use load or switch on their own local generation. Well, yeah, that's about the introductory thing. This is a very abstract view of the connected part. So I said functional programs connected to the power grid. I'm reading this sentence backwards. So now I'm coming to the connected part. Like at the center is the public internet with a VPN tunnel. So we are not using an overlay network. We just have consumer lines, which is new for the energy thing. And then we have two network operation centers where people are doing things, and also our servers are located, and we have a data redundancy for failover. And the TSOs, so the transmission system operators who need energy to balance the grid, they send us signal over some energy-specific network protocol. It's called IC 60875.104. And so this is the protocol you use to control nuclear power stations also. Everything in the energy world in Germany works with this. And when they do, so they send us a request, and then we decide what to do here in these network operation centers. And then we put out demands or requests, actually requests, to our e-boxes, which are directly connected to the PLCs of the production company. So if we click a button, it may happen that really the paper mills reduces in power. So like 1 of 10 production lines just goes to the meter. Okay, so to give an impression how that might look, that's the network operation center, and that's an e-box, and yeah, it's a field box connection to our participants. And the other thing is we need to communicate with these boxes, and depending on the participants, it's either wired or wireless with GSM or UMTS or whatever for machine-to-machine communication, and that actually creates problems in its own right. So from now on, I'm going to a command line mode. So there's a lot of text on the slide. Don't mind if you can't read it all. I'll explain the highlights. So what are the requirements with the broadest view? So the requirements are that we have a back office system, which is a soft real-time system. So soft real-time system is not very well defined, and I leave it at that. But it needs to answer, and I like the definition Frank McCabe gave us. So something that answers in a time that makes a difference to what you want to do. So if it takes 1 hour to compute something that you need in 1 minute, then it might not be the real-time system you were looking for. But our system samples a couple of times a minute. It samples what is going on at the factory, and then it acquires this for a number of all our participants, and then if you want to switch, it sends these signals back to the facility. Now, there's also a front office system with a soft real-time GUI, and this system is soft real-time in this sense, and that might be new for functional programming because the operator is in the loop. So you get a request from external parties, and then you need to do something under time pressure, like, okay, switch, and go, and that needs a user interface that works in real time in the sense that it doesn't hang up, or it doesn't take a minute to do things. Yeah? And that's the important thing. I see I'm already over time.
No, 10 minutes.
10 minutes. All right. Okay.
We started late.
All right.
Got some buffer time at the end. So.
Okay. Now these are the two most important things, and having a real-time GUI. And then there are other essential things like, okay, we need the communication, we need a field bus interface, we need an embedded system, and most of all, the back office system is running unsupervised. So essentially, we don't have people who are checking 24 hours that they are still running, so they need to recover in auto restart on different levels of it. And there's lots of additional functionality. Right. So I'm now explaining a little bit of our technology choices to come to the FP part as well. So our first choice of the embedded platform turned out to be unlucky. And if you run an industrial project or any project, actually, you know that can happen. So eventually we dropped this supplier because they couldn't fix their product, which was a shame and put us back a couple of months. And the second choice was the second round was a lucky choice, and it was a little box that came with a Linux, and on the Linux was Python. And then I decided, okay, our performance requirements on this embedded system are not that high. In fact, they are quite low for embedded systems. So we could use everything do everything in Python, and that's what we did. And then if you do it in Python on the embedded side, why not use it on the server side? And that turned out to be a good choice because we had 99% overlap in code on both sides, and that reduced our development cycle quite enormously. The Python code is for a large part written in functional style, but I'm not talking about replacing the built-in for by a lambda or a generator or something like that, but we are very conscious about using state if you don't have to, don't you? So the client-side GUI, the initial boundary conditions set by the board essentially said it must be in .NET on Windows. That's, well, and you can question, is the language important or is it not? And it wasn't, so why not use F#? And the other thing is, for a GUI, you need a GUI toolkit, and at that time there was WinForms or WPF, Windows Presentation Framework, and we chose for the more modern-looking thing, which was a choice. And one important thing is we outsourced this development for a very large part, and the party who we were outsourcing to were actually experts in functional reactive programming, and that turned out to be a good choice as well. So, well, but time has, or things, specifications evolve, and it turned out that we want to redesign the server-side core and scalability along various dimensions. So scalability is also often understood in a one-dimensional way, like you have more customers or you have more records in the database and stuff like that. We have several dimensions in which it must scale, and to be honest, we don't know in advance which direction it will scale and in which it doesn't. For example, in the direction of participants, we expected it to scale by 2 orders of magnitude and it didn't. And on the other hand, in the direction of sample rate, like sampling it more frequently, it did scale by an order of magnitude and we didn't expect it. So this is why I take quite a flexible approach to that. And also the thread concurrency in Python, it can be made to work, but for a real-time system, it's thin ice. So this made us look for Erlang OTP, which was my ideal candidate from the start, but under time pressure it might not be a good way to introduce a completely new thing also if you have the application domain still not under control. And Python will stay with us. So there are some functions that we are not going to move away. On the other side, the redesign on the client side, that is, the program works well as it is, but the requirements have changed considerably. So initially it was envisioned as something where you have quite a lot of user interaction in real time, and it turned out you need less user interaction, but you need more frequent updates. And yeah, today I learned using cursors and a text interface. Actually, I didn't even think of it, but I'm pretty sure if I had thought of it, it wouldn't have gone through, because as a startup company in this business, we need to have flashy user interfaces, and it's sort of hard stale. But if you use it only internally, then it's really, I think it's really a very good choice. And it frees resources enormously, because user interface stuff, GUI stuff, oh well. Yeah. Well, unfortunately, the rich client that we have is also the only component of the system that sometimes relapses below quality level where you can roll out, and that tells us less about the program itself as more about the testing procedures that we have in place to find it in the first place, right? And it's not a big issue because we only have very, very few users, and so we can get back, fix it, and make it to work, and improve the performance issues, and then that's it. Okay, some random bits of experience with the three major technologies that we use. Python has served us well, certainly. And okay, there's very little I need to tell you about Python, I guess. But one thing is it's a relatively steep ascent from a prototype, where you cobble together a script, to something that you want to use in production in 1 year from now. And it's still there in 1 year from now. And on the other hand, in Erlang, I find that exactly the opposite. Once you're done with a prototype, it's nearly production quality. I don't know how that is possible, but it's like that. Yeah, it's a good thing. And also modularization, so that shows me that modularization is working. So the module, not in the sense of a module system, because all these programming languages have a module system, but the fact that you can put some functionality into a container and reuse it later, that seems to work best of all these languages with Erlang or GP. I don't know why again, but it's the process. You have a process, you know what this gen server or whatever does, and sort of 1 year later it's still there. And with F# WPF, it's a bit difficult for me to judge which parts are attributable to which part of the technology. It was a good fit with the original concept. We want to get away from the rich client idea and have a complete web interface. In practice, at least I find it hard to modify or correct other people's code. And that has to do with the fact that there are so many different ways of expressing the same thoughts in the code. Like you could use monadic style, or you could do not, or you could wrap it in functions, you can parse it through things, and on the syntactic level. So often it's like, okay, I'm not asking myself, what does this function do? I'm asking myself, is this a function? And so that's sort of a problematic thing. I mean, in Erlang, it's like, it was much easier, very shorter cycle to establish a common understanding of how we do things within our development. There was some friction, but we did establish it, and then from then on there was no discussions on that anymore. All right, that already brings me to the summary. So, like, what challenge in the national power grid do we actually address? And it's like the intelligent management of industrial consumers for grid stability. And in theory, this is old hat. I mean, people did that in a way 30 years ago. In practice, it's really, really difficult. And also, we are probably not the last who will try, and it's also not clear if we will succeed. I mean, we have an operation, but it must be commercially viable and it must stay so. And these prices in the auctions, for example, where the reserve energy is auctioned, are very, very volatile, which is a problem in its own right. And yeah, what are the main challenges? To maintain a soft real-time system with a man in the loop, which is sort of a new thing, at least for me, and tracking a very fast-paced requirements environment. Yeah, often requirements are verbalized at the moment when the software is rolled out, which might be a little late in the process. But so far we didn't sort of veer too far away from the path of good faith. And well, yeah, how does FP help us? And I can only say I don't think we would have been able to do with the resources that we had what we actually accomplished in terms of software functionality and stability. And that's the main message I have today.